Hello. So today's lecture I will give it as a video because I'm not sure to be able to give it live at 2 tomorrow. But I mean it's the same, right? Since it's anyway online. We'll start the lecture by giving a small compliment for the result of last week, where we showed that the quantum Fisher information is a convex roof of the variance, right? And on the other hand, we'll just now quickly show that while Fisher information is the minimal average variance of the ensemble of pure states in which the density matrix decomposes, right? It's also always upper bounded by the variance. And this is very simple. So basically what we want to show is that if you have a state curve rho of B, right, then the quantum Fisher information of rho of B is smaller, we call them 4 times the variance of the state rho on the operator H. Yes? So the variance here is just H, so let me just write it. So trace of rho H square minus trace of rho H square. Right? So I'll just write it down as H. Alright. H square like this minus average H square. This is the two terms we have in the variance. So let us show this. Display quite well. Good. So this will be just a first warm-up, and you will actually, I think in key we'll use it later in the exercises to explain the last point how to interpret it. So it's nice. I just realized that we didn't prove it, but it's very simple. So let's do it. So how do we do this? Well, all right. So what we've seen last week. Let's take our density matrix, right? And now we decompose it as an ensemble of pure states, Pi, and the pure state phi I. So right, there are many decompositions like this, and we know that for the quantum Fisher information, yes, we know that the quantum Fisher information of the state rho. Now here I mean, of course, with the Hamiltonian H. So this is the quantum Fisher information with respect to the unitary evolution generated by the Hamiltonian. Yes, so I'll write it like this. Well, we know that this thing is smaller or equal than the average variance. Okay? The average variance, which is sum of the variance of the pure state psi I on the Hamiltonian H, right? So how do we know it? Well, it's with a forecast here, right? We just know it from complexity. For all the Fisher information, right? So we obviously know that Fisher information, right, of sum of Pi psi I by complexity, this is smaller or equal than the sum of Pi of Fisher information of psi I, okay, of each pure state. And this thing is just equal to 4 times the variance of the state with respect to H. Good? And of course we also know it because we know that Fisher information is given by the minimum of this quantity. Right? So of course for all the other decompositions it's larger. Well, so to show that the variance of this thing now, what we want to show is that the variance of rho on the Hamiltonian is larger than the Fisher information for rho on the Hamiltonian. Well, and this to show it, actually we're going to show that the variance of F is larger than the average variance for any decomposition. Okay? So let's do it. So let's first write down the variance of a density matrix. So we have a density matrix, and this is the variance of the density matrix on the H. This is just given by well, the average H square. All right, so the average H square trace of H square on rho minus the average H squared, right, which is trace of H on rho squared. Okay? Yeah, this is what we have from here. Now we do the same thing as the average variance for each decomposition. So what is the average variance for each decomposition? Say I. Well, this is simply trace of sum of Pi, trace of H squared psi I Okay. Well, what you see here is that the second moment first here is linear, so we can just rewrite it by putting the sum inside the trace, right? Trace is linear, so the trace of, here we get the trace of h squared, sum of pi, sum of I on psi I with a weight, right? So here is precisely rho minus this. Here we cannot do this because obviously here we have a square, right? So we cannot put the probability inside. Instead we will denote this object simply as this is sum of pi, all right? And here we call this thing as hi, so it's absolute value I squared. So by this we mean it's really the absolute, it's the expected value of h on the i's pure state in the decomposition. So what we get is trace of rho h squared minus sum of pi hi squared. All right. That's already good because we managed to identify the first term, right? We call that here we get this minus this. Now it remains to show how these two are related. The expected value of h on rho squared and the expected value on this thing here. And yes, to do this, what we have is, in fact, if you develop this term here, right? So we can develop it further because we will have it sum inside. So this term here is, let me just have a small place here, trace of h rho square. Well, we just write down our decomposition. This is the sum. So this is the sum of I of trace h pi psi I square, or in other words, here what we get is really the sum of h i's. Yes. So each trace here is precisely, put the pi out, this is precisely the expected value of the Hamiltonian on the E state. So here we get sum of pi hi squared. So to summarize this thing, I will just write it down again. This is blue well, looks like yes. Yeah, so and then we conclude our proof. Using again the Hilbert-Schmidt, sorry, the Cauchy-Schwarz inequality. So we get the variance of h on rho is trace of rho h squared minus sum of pi hi, right? Again, this is the expected value on the i's pure state in the decomposition form, and the average variance and the average variance of pi variance of h psi I. This is the same story, trace of rho h squared minus, now this term is different. pi hi squared. Okay. Well, now to relate this, we use again this the Cauchy-Schwarz inequality, and to do this, it's very powerful to do this. We look at this as a vector again, or better look on this as a vector. Okay, as a scalar product of the vectors. So what is the scalar product here? I will pick the following one, but let's decompose it as this. So let's see sum of pi hi, right? Check. This we can see it as sum of I pi square root hi times square root of pi. Yes. Well, it's just a trivial statement, but now by writing it like this, we can see that this is now a scalar product between a vector with components square root of pi and hi here, the expected value, right? This vector times the other vector we just has pi's. Okay? Square root of pi's as entries. Now we know by a Cauchy-Schwarz inequality that this is the overlap of two vectors. Of course, this overlap is bounded by so the scalar product of the vectors is always smaller or equal than the norm of the vectors. Yes? So this is smaller or equal than the norm of this first vector with elements pi hi, and the norm of the other vector with elements root of pi. And of course, if it takes absolute value, let's take the absolute value everywhere, because you see here we have a square. So we're allowed to do so. Finally, if you develop this term now, so what is this norm? So, well, this is easy. Because the norm of this vector is just the sum of pi's, so it's 1. Right? So this norm is simply 1. And this norm is sum of pi, square root of pi times square root of pi times hi squared. Alright? So what do we show here? We show that this term here, yeah, of course with the square root, right? It's a norm. Yes, so this term here is the sum of pi's expected value of is upper bounded by this guy here. Okay? Now we'll take a square here, so here we have a square. Square removes the square root from this guy. And we get what we want. So we can just write it down compactly. This thing here is smaller or equal, and this term here, sum of pi, hi squared. Nice. So, finally, what does it tell us? Well, these guys are equal here. The sum is equal, and then this term is larger than this term, but because it comes with a minus sign, this thing now is smaller than this thing, right? So this implies that precisely the variance of the operator h of the density matrix h for the Hamiltonian of the density matrix rho for the Hamiltonian h is larger or equal than the average variance for any decomposition. Okay. All right. Yes, this is what we wanted to show. Yes, we show it directly. In fact, we know more. So, in fact, kind of what happens is that this is not a saturable. So there exists always a decomposition for which this equality is tight. So, but we don't need it. But maybe you'd like to know it. So, whereas the Fisher information gives us the minimal variance, the Fisher information of rho is the minimal average variance of any decomposition. Actually, the variance of rho itself is a maximal average decomposition variance. Good? So this was a warm-up. You will need it for the exercises, but it's also nice to sort of, yes, last week we related the Fisher information of rho to the variance of decompositions. Now we also relate the variance of rho to the variance of decomposition. We will see it in the exercises because it's very nice for the reason that it allows to rewrite kind of Fisher information uncertainty relation as a refinement of the usual Eisenberg uncertainty relation. So refinement meaning it's more powerful. It gives us most information. You will see it in the exercises in key. Okay. So this was just a short reminder. No, not actually a reminder, but more warm up and something you will lose later on. Now we can start the lecture proper for today. And the lecture will be, we will come back to our estimation business. Okay. And today it will be for lecture 10. Alright, this is actually Bayesian quantum parameter estimation. Parameter estimation. Okay, and well, in brackets I can say beyond QFI. So far we're talking about parameter estimation. We always had this framework. In the very beginning, if you remember, we talked a bit about Bayesian, the Bayes formula. But then we jumped to this estimator formulas, where an estimator has a variance which is dictated by this Cramér bound, and which is upper bounded by the Fisher information, right? So today we'll come back to this very original story, where QFI is not everything we need to know about the state. So let me just remind you what we have so far and how we consider things so far. So now we have this big space of states, whereas this is possible states for rho, and our model, right? So our parametric model is a curve inside this space. It's just a one-dimensional curve because we really all the semester we only consider single parameters, so scalar parameter estimation. Yes. And so far what we said always is that yes, at the end, what we care about is that we know that the true value kind of is here around some b, yes? And the error with which we estimate b, if the true value is b, ultimately is dictated by the Cramer-Rao bound. So Cramer-Rao bound, remember Cramer-Rao bound tells us that the error on the estimator, so delta b, or I think we denote it mean squared error. So the average deviation of the estimator from the true value of the field cannot be smaller than 1 over the Fisher information. So for quantum state, this will be the Fisher information of rho. Okay? So what does it mean? Let's think about it. You think about it, of course, this property here, the Fisher information of the state at B, actually it's a local property, right? It's really a property only around this point, because it only depends on the state here, how it looks like, and the first derivative. So this quantity really doesn't know about the curve at all. Actually, it only knows about the neighborhood of the true value. So how does this bound hold? Well, it holds because actually ultimately, as follows from this theorem, Cramer-Rao theorem, ultimately when you estimate many times, right? You will only you will shrink your knowledge of the parameter to this point, and then the only thing which will matter is really how the curve behaves in the neighborhood of this point. Yes? And since we know that this bound is attainable, so if you do many repetitions, we will get this precision. It tells us that this is really what matters. But on top of it, it also tells us that even if we are not in the, so even if it's for one measurement, you can still not estimate better than this. But in fact, you can estimate much worse, right? So this is always a lower bound on the error, but it can be a bad lower bound. It only becomes tight when we have many repetitions. And kind of the general logic why in many repetitions what matters is really just the Fisher information of the state here. This is some kind of very general statement in estimation theory, right? It really comes from the fact that the prior information, so all this kind of prior knowledge of the curve, at the end doesn't matter. The only thing which matters is local properties here around this point, right? Will always bring down. And this you can look at it, for example, for Bernstein-von Modest theorem, which is precisely a generic result of this type on any kind of Bayesian estimation, right? So this is what we did so far. We're looking at this problem in the neighborhood of a point, in fact. Yes. So now, what do we do generally now? Suppose that. And what will you do if you're not around it? If you're not in the asymptotic regime and we want to do something better than the Cramer-Rao bound? Yes? So how do we do it? Well, then, two things are important. Well, first, it's still true that we have this kind of parametric model, right? So parametric model, let us go back to the classical thing first. So parametric model, right, it's really just a probability of the outcomes conditional on the value of the parameter. So in our case, it's B, right? Parametric model. So this tells us, in our story, how the measurement result X is related to the value of the field. We need such a thing for estimation, right? Because we need to know the physics of the system, the physics of our probe. How does the measurement result relate to what we want to estimate? So one thing, however, now what is different, and this was enough for quantum Fisher information, right? It was anything which mattered. But now if you want to estimate, if you want to really consider the full problem in a Bayesian way with a single shot, then we also need some prior knowledge, or prior distribution, okay? Prior distribution. So what is a prior distribution? Again, we mentioned it a little bit before in one of the first lectures. This is just a distribution of the parameter, right? A probability distribution which actually tells us what we know about the parameter to start with. Okay, so now if we what does it mean? It means if we unwrap now this curve, right, this curve in B, we can kind of unwrap it, draw this line, so let's take it like this here. Well, so this is our B, right? So B goes from somewhere here to here. For example. Yes, and the prior knowledge now is just a distribution. So for example, typical, I don't know, we can have a Gaussian distribution as a common prior knowledge. So this distribution supposedly captures our belief about what the value of the parameter could be even before we estimate. Yes.
So the cleanest way really to think about it is thinking of a scenario where I'm the one who measures. Let's say I'm Alice, right? I measure the parameter. So I observe this result x, and the other person, Bob, who prepares the parameter, he really just draws it from this probability distribution P0 B. So we know the procedure exactly, except of course the value. So we know that the parameter will be in this interval, and it will be generated with this probability distribution. Right? But of course we don't know where it is. So this is the prior knowledge, yes? So these two are now, if you really want to talk about Bayesian distribution, these two are the important things now. So as compared to what we had before, we add this prior distribution P0B. And again, for asymptotically many repetitions, this is a general theorem, the prior distribution doesn't matter. So that's why before we could completely avoid it and everything was nice. Yes, so now the question is, what do we do once we observe an outcome? Yeah, so now we have this prior distribution, now we have, and then we do a measurement, right, and we observe some outcome x. Measurement outcome x. So in other words, we take our probe, right, interact it with the environment which we want to measure. It encoded some this parameter b, then we get a measurement output, and we want to know how good is this estimate, what is the value of b. Well, this is, so now what we do this now is in the Bayesian problem like this is in fact we update our knowledge. Yes. So what we care about really is now probability of b knowing x, because we observe x. So how to compute this thing? Well, again we can use bias rule as before. So the probability of b knowing x, this is just joint probability, right? This is two random variables. We can look at it this way, because now b really is a random variable which is prepared from this probability distribution, right? From the prior, so we just the joint probability divided by the probability of x. Right? This is really the definition of the conditional probability. Okay. What is more, that we can further decompose it as being equal by 2, 3. Right? Again, we use bias rule again to get, now this is x conditional b times probability of b, which is a prior probability, right? This is the probability of the value of b divided by p of x. You see? So if I erase this is really what we need now, because the missing. So this is the two ingredients we have, right? Our parametric model, how the measurement outputs probabilities are related to the value of the parameter. This is the prior knowledge. Now this thing p of x here. In fact, we can also compute it on this one, because p of x is just simply right. What is it? It's probability of x null b times p of b, but you have to integrate over b. So in other words, well, since the probability of observing an outcome, we can just simply compute it by knowing that we know exactly how b is distributed, and for each b we know what is the probability of x. So if you do the convolution, we just really get the probability of this thing. So if well, maybe there is no space, so I can now erase it. Actually, let me keep it here. I just will write this maybe bigger because I'm sure you see this. No, you think you do, yeah? So, by doing this story now, right, applying the bias rule, from the two things we know, which describe our model, the parametric, the relation between the outputs of the physics and the prior, we have a rule of how to update our knowledge of the parameter once we get the measurement outcome. Okay. Yep, well, that's almost it for the general story. One more thing is that, let me just write it here. So, so in our model, right, we have p of x knowing b, and p0 is a prior b, right, and then the output kind of, right, the output is at the x. Our measurement result gives us this new updated knowledge of p knowing x. What's not clear so far still is, okay, we have it, it's very nice. In principle now we know, so we update our belief, we know how the parameter is distributed, This is our best guess of the parameter distribution once you observe the outcome. But it's still not clear how to tell which strategy, which estimation strategy is better. So in other words, we would like to, for all this family of distributions for different outcomes, we would like to give it a score. We would like to say, is it a good distribution or a bad distribution, right? Like before we had just a variance, and this was very nice because it's just a scalar number. So same thing we want to do here, and to this we just introduce a score. Same story. So we just introduce a score, right? And the score will be simply score. So it's a score function. Score function just takes this probability of p, right, and gives it a score Sx, right? And then what we care about is the average score. So the average score S average. Let's just write it like this. Let's call it average score. This is average score. This is just S, which is average S for all x, and this is just simply what is it. Before we do the estimation, we can, since we know the model, we can compute the expected score. So how good our estimation will be once we do it. So it's just the sum of all possible outcomes, right? P of x times Sx. Yeah. So in other words, before even we do the estimation, we can already compute this thing, and we can say, okay, for this, for example, for this estimation protocol, we will get this expected score. For the other estimation protocol, we will get this expected score. So of course I will go for the one where the score is larger or lower. If kind of, no, then it will not be a score, but kind of a cost function. So one nice score, which is actually more the cost function, is the variance. Right? So this is kind of the general story. So the variance is again as before. So variance is a score. Yes. Yes, so one thing we can care about, and this relates very nicely to what we had before, is that for this distribution P of B, I can just attribute it to variance. So let's call it V of x. And V of x is just the integral of P of B of x times B, right? The value minus the average B for x dB. Okay? So where is this guy here, V of x, is kind of our estimator. Sorry, that's correct. Yeah. So if you draw it now, we have our, what is the idea now? Let me just summarize it maybe graphically. So the idea is as follows. We had some prior distribution. This is B. Right? We had some prior distribution. For example, nice Gaussian like this. Then we observe some outcome, x, and we update it, because we update the probability node. And then we get, for example, something sharper. Yes. So this is P0 of prior distribution of B, and now we update it. So this will be P of B knowing our outcome. Yes? Yes. And of course, depending on x, it might be centered differently. So if we have this probability distribution, of course, if you want to estimate B now, we will just output the average value. We'll output this B of x. But whatever we output, now the variance, so the deviation of the true value of the field from our estimator will be given by this variance. But of course, the optimal estimator is just simply to take this story, right? So just to simply take the average B. This is actually the score we'll care about in today's lesson. Yes. It's interesting to just, if you think about it, how does it relate to our previous formulas with estimators and fish information? So you see here what we compute, because we keep track of all the probabilities of how the parameter is distributed. What we compute here is actually the average deviation, square deviation of the true value of the field from our best bet, right, for x. So it's really, this variance here really gives us the variance of the final knowledge of B we have. So it's also, while before we actually had an average deviation of the random variable, which was the estimator. So here actually the estimator is fixed for x. We know its value because we know how it relates, and we compute the variance of the true parameter. And before we actually computing the statistical variance of the estimator. Because we didn't know, because we anyway assumed that the value was known, right? We really were looking at the problem and the neighborhood of a point. But otherwise it's kind of still the same figure of merit, it's a variance. So they're kind of nicely related. Yes, so that's it for kind of the classical part of it, right? I mean, it's pretty similar. The general line is similar. We have this thing we want to estimate. We have the model, and additionally we have the prior. Now we have to tell something about the quantum case, yes? And we'll see how things are different for the quantum case. So of course, V of x is variance for V. We also have variance, which is just sum of P of x, V of x. This is the average score for all possible values of the parameter. Nice. Good. So let's now, having all this stuff in mind, we will now explicitly consider quantum estimation. Okay. So let's add here that in this small square here, that the variance of this posterior distribution B now in X is our figure of merit. Right, so of course when we want to choose which estimation strategy to use, we will choose the one for which the expected variance is the least. So now consider so quantum latent estimation. So what is different from quantum latent estimation? Well, the prior is the same, right? It's prior has nothing quantum. It's really just our belief in the value of the parameter can take. So P0 of B isn't changed. Now, of course, this thing again, the parametric model becomes different because it becomes quantum. Now the parametric model. So this is stays the same. Stays the same. But the parametric model now, of course, is different because now compared to the classical case where we just had measurement outcome which was dictated by the parameter value, now we have a state first. So we have the state of the probe, rho of B, yes, and then we have to choose a measurement to get the outcome x. So again, this relation between the value of the parameter and the x is not trivial. Precisely because in quantum physics we have a trivial relation between the state of the system and what we can read out from the system. So this thing now becomes, as before, so this I'm sure you now understand very well. The parametric model now becomes a curve, not in the state of probability distributions, but in the state of quantum, in the space of quantum states. And again, we have to now choose the best measurement in order to do this. In order to do this, in order to do what? In order to minimize precisely this expected variance. So we want to find in general now the problem is kind of complicated because now we have to explicitly consider kind of all possible measurements here, and for each of them we will compute this average expected variance, and then we would like to see what is the best possible measurement to choose in order to do so. And this is even before considering what is the optimal state to plug in. Right? You see, so it's not simple a priori. But again, there are some general rules and general results we can have. Alright, so this I think is clear. This is what is different in the quantum case. Just as before, in the quantum case, the model is a state of a curve in a space of density matters. So to get some intuition and to start, we can actually, there is one nice case which one can solve explicitly, and this is a case which is constructed as a variance and with projective measurements. So let's write it down now. Let's say so now best average variance. This is 3. Best average variance and projective measurement.
So it's nice because it's one of the rare cases which you can solve explicitly and get the best measurement in a very nice form. So it's a good idea to get some intuition about this thing. But then we'll move on to some more general bounds. Because in general the problem is hard to solve, but we can have some results as before. You know, before okay, QFI is a good figure of merit for estimation. Now there's something more here. Within there are more, but first let's start with this to build up some intuition. So now the assumption here is, first of all, of course, that for the score we'll use the variance. So our score will be this average variance, right, which is given by sum of P of x. Just write it down. So P probability of the outcome x times the variance. So times the integral, right, of the variance. So variance is P, this conditional distribution PB of x. We'll take here on the line. So our score, sum of P of x, the outcome x, the variance for the outcome x, and this is just sum of x, probability to get the outcome x, right, in our final measurement, times the variance of the distribution conditional on x, and this variance is really just P of B conditional on x times this true value of the field minus our best estimator square. Yeah? Yes. Nice. This is what we want to minimize. This is our question. Now we introduce an additional assumption, and the additional assumption will tell us that right, is that when we have our state rho B, the measurement is a projected measurement. So this PVM here, which we'll use to extract our random variable to obtain the measurement outcome x, is a function. So it's made of 1D projectors, orthogonal 1D projectors, right? So it defines a basis in the Hilbert space. Right? So it's, let's say, k, some basis k going from 1 to d. If d is the dimension of the Hilbert space in which we are doing our quantum model. So what happens there? So now you see, here what we have is Bx is the best estimator of B given the value x. So now here the outcome of the measurement is labeled by k. So to each k we can again attribute the value bk in the same way. This is just a number which supposedly will, so in the best case actually attributing this thing will just correspond to the average of this probability distribution, the average B for this probability distribution. But let's keep it open for the moment. Because if things are right, we can just optimize this value here, and this will bring us to the least possible variance. So so far we just think of it as, okay, I observe the value k here, and I get then let's say the field is bk, and I will keep this value bk for free for the moment. So what's nice now? That now we can define. Right, so they have a basis, we have the value for each element, so now we can define an observable. Right? So we will just define observable S, which basically combines in a very nice form, compactly, this basis choice, which in principle can be arbitrary for the POM, and the estimator for each k. I'll just define it as being the usual thing, right? So this is sum of k, bk, 1 to d. So right, so if you write it in this basis in which the PVM transforms, it's really just bk values on the diagonal of the matrix. Alright, and now with this S operator, which for the moment is arbitrary, I can define two quantities which are operator gamma, so we need it here, and now we also have this operator S, which is just given by sum projectors in our basis times estimator bk 1 to b. Yeah. Now we'll define two more operators. So what is the best way to prove it? Yeah, I'll just give you the definition, then we prove what we want. I think it's simple. So we define two new operators. The first one is simply just no, actually no, let's do it differently. Let's really work with this expression and try to rewrite it. So let's see what this is. So now we just compute first the sum and the integral, so we have the dv, right, sum over x here. And then we have p of x, the probability of b knowing x times this variant b minus bx squared, yes? So far I did nothing, I just put it all together. Now if you look at this expression clearly, this thing, using the Bayes rule, this is just the joint probability, p of b and x, because it's a conditional on x times x, so we just replace it. Check. Here, because the whiteboard is quite small, so here we get p of b, so the joint probability to have enough to observe the outcome x, and that the field is of the value, the field value is b. Okay, now again using Bayes rule again, this thing is just the other conditional probability which we know. So this is p of x knowing b, right, times p0 of b. Okay? Yes, very nice expression. Now why is it so nice? Because we know all elements here. This is our model. This is the prior of the model. In addition, now we can express it because we know we have defined a measurement. To fix this measurement, you then S. So now with this, if you measure really in this basis, then what we get is of course p. So p is just given by the Born rule. X conditional to b is just trace. So x is k now of, let's say this x. So x is just the value of the k, right? Times the density matrix rho. So rho b, of course, is always our parametric model. We have the back of our mind. This is how the states depend on the parameter. So now, on the big curve. Okay, so let's plug it back here. So this thing is just the integral of the sum of x of trace of x rho b times, yeah, there's no place. Rho b sum over x, and this guy here, just expressed this before, this is trace of x times rho b p0 of b and b minus bx squared. Nice. Now let's just without this the sum, so we had this index x here, we can also write k. Just too much notation here of the operator. It's just an index, so it doesn't matter how I call it. Yes, and this is not all, because again we can simplify this, and to do this we will expand this story here. So this is b, right? The square is b minus 2 bx bar b plus bx bar squared. Yeah. So let me write it all together now, and what we get finally, and we put everything inside the trace. In principle, trace we can always put it out, this is just numbers. So now we have the trace of what? Which kind of object? We have the trace of sum of k times b squared minus 2 bk bar b plus bk squared. And what is missing here is rho of b, the state for the value of the field b, and the prior distribution p0 of b. And of course an integral. Yep. Yes. So, bear in mind, this is what we have here is the average, is our average variance of the final expected probability distribution. So actually now there is not much to be done because what we want is to make appear this operator S here. And to do this, you see the only thing which depends on K is just this BK here and the projector. So again, let's write it down here. V is equal to it's integral over dB, sum over K, and the first term is KK, simply sum of KK. Yes. Some. Yeah, no, it's actually good idea. So sum of KK. So let me just write these three terms here in three different lines. Okay, so we have the integral, the integral, and the sum of K everywhere. And then we have, first thing we have is big brackets. Big brackets like this is KK times B square times rho B times B0 of D, right? Minus KK BK 2 times B rho B and the probability, the prior probability, plus KK BK square bar here, it says estimated, times, well, the main, so rho B B0 of D, yes. That's our three terms. Well, first, now what we do is I pass the sum inside, sum of K. Well, you see that basically, for the first time we have a sum of K over our betas, and of course it just gives us identity, okay? Because there is nothing else which depends on K. So this term here is just identity, and the identity we can forget about it because there is also a trace. So the trace identity times density matrix, this is just the density matrix. So forget about it. Now the second term is precisely our operator here. So this is the trace of our operator S, observable S, on the density matrix. So this is S. Nice. Now this guy, what it is in principle, yeah, this thing is just S squared. Why? Because S is made of orthogonal projection, so it has this thing there. So S is just an operator which has BK on the diagonal, and this guy has BK squared on the diagonal. Yeah. So this thing is squared. This is actually where the assumption of von Neumann measurements comes into our story here, because we are only able to do this trick if we really measure if our QM is made of orthogonal rank 1 projectors, because then the square of S just gives us this thing. Otherwise we couldn't play this trick, but here we can. Yeah? So because S is defined like this, so we get S squared. So now you see we had some nice. It's convergent to what we want. It's convergent to what we want because we're able to write down the story, the average variance, which we want to minimize for our strategy, as the sum of returns, and these returns are, we have the trace. Now let's put the trace out again. We have the trace of the integral of dB B square rho B, so B0 of B rho B minus integral of dB B rho B B0 of B times S 2 times, and plus finally integral of dB rho B P0 of B S squared. Okay, that's it. Those returns. And finally, we can take out the trace, actually. Or not the trace, but here we can take out the trace already, because you see this is just numbers, so the trace here is just here, and the trace of rho is just 1. Okay? So if I take the trace out of here and I put it in each term individually, we'll have a trace here and a trace here.
Then the first term, just there is nothing, there is no operators anymore. We trace out the density matrix. Right? But what is left is the expected value of b squared on the prior distribution. So this thing is b squared. Alright? Good. And this is now the last line. Alright? And then get there. Because now we get to a point. The expected variance is really given by b squared, the expected value of the b on the prior distribution. Let's put it 0 here, maybe, right? To just say that this is really the second moment of the field on the prior, minus, you see, 2 times trace of s times the integral of db. Okay, and this thing we'll call this operator gamma. So gamma is just basically kind of the average density matrix for all the b, for all possible values. Finally, the last term is plus, the same story. Plus trace of s squared. Wait a second, yeah, there was a b here. Okay, so this we'll call it eta. I mixed up, it's just a name, but this is how I call them in the note. And this will be db p0 of b times rho b. Yeah. And this we'll call it gamma. So somehow we managed to express all this a priori complicated story by introducing this operator S, which captures both the estimators of the field and the basis in which we do it, and defining 2 new operators which are just defined basically by the model, so by the curve of the density matrices here and the prior distribution. Yes. So just to write it in the more complex thing, we have this is minus 2 eta s, so trace of eta s plus trace of gamma s squared. And where the gamma is equal to the average density matrix, and eta is given by kind of the first same story but with a b times the density matrix. So this right here with these operators we can just compute them once we have the prior and have a model. So we know both of the things. We compute the operators, they actually define our problem, and from this we can move on. Now the funny thing again is you see there are kind of just 2, like as before we had the density matrix and the first derivative which completely define the problem. Here we have a bit the same story, so the operators are different. We have our gamma, right, which we just compute as the average density matrix, average in the sense over all possible values of b with the prior distribution, and kind of the first moment of the density matrix. So we just start with the derivative. Yes. And you will see it's really a very similar structure. The problem, why? Because of the following thing. What do we want now? What do we care about? Well, what we care about is the minimum possible variance. So now we have all measurements. So we remotely have measurement strategies. Strategies are only captured by the basis choice, k, and the values, vk. Yes. So basically, all the measurement strategies, they correspond to all possible observables, right? So they correspond to all possible observables, as observables mean they are emission. Yes? Observables mean they are emission. So what we want now is actually to minimize this expected variance over all possible measurement strategies, but now it's equivalent to minimize this expression here over all possible emission operators. Alright? This is kind of the beauty of this thing. Why? Because minimizing over all possible emission operators is actually simple. You can just use what we know from calculus, except on space of operators. So what we do now is we just have an operator S, and we consider a small, we just move it closer. So we go from S, we go to S plus delta sum, well maybe let's not take some G, right? So in the space of kind of emission operators, we just add a smaller emission operator, and if we have the minimal value of the variance,
Then when we do the shift, well, this derivative should be 0, right? Because it means that we hit the local minimum. Okay? So let's just do it. So this is how is it called? So it's really the most trivial minimization problem we can have, right? We just check that it's local minimum. So let's do it. So what does it mean? Okay, so that S goes to S plus delta G. Alright? Let's see how this expression is affected. So we'll call it this is the variance for the measurement strategy S. What is the variance for the measurement strategy S plus delta G? Right? And of course we do it just to the first order in delta. Delta is a small parameter. And G is any Hermitian operator. Because we can shift this observable in any Hermitian operator direction. Yes, so what is this? Well, of course, this guy doesn't even depend on S, so it just disappears. This guy will get minus 2 trace of eta times S plus delta G. Alright? Alright. And from this term, it's a bit more complicated. We get plus trace of gamma, and here we get S. So if we expand this, okay, let's just do it right now. S plus delta G times S plus delta G. Yeah. So to the first order, this thing is S squared plus delta SG plus GS plus delta squared something. Delta squared is squared. So we don't care about this, and we don't care about this because we only care about how this expression moves with respect to this. So this guy becomes plus trace of gamma times SG plus GS. Alright? So in other words, our condition for optimality now, so D, how do we write it? Let's look at this. D over D delta of V of S plus delta G is equal to 0 for all G Hermitian. This is equivalent that this thing is equal to 0. So this thing is equal to 0. In other words, this is trace of G. Yes, no, it's impossible to look at. Okay. So this term is equal to this term. So trace of gamma SG plus GS is equal to 2 times trace of eta S. Yeah. Sorry, eta G, of course. Yeah, this term is zero. It doesn't show up in the first order, it's 0. This is the same. Now let me write it a little bit, so we'll see how nicely it comes at the end. We'll just reshuffle it using the sagacity of the trace. So this condition, right? So local extremum condition is equivalent to having, if we write it a little bit, we'll just get here trace of gamma S plus S gamma times G is equal to trace of eta times G, right? Now remember, this has to hold for all operators, Hermitian operators G, right? So the trace of an operator over any G should be equal to the trace of another operator over any G. And because it has to hold for any G, this is, right? This is the same as just saying that gamma S plus S gamma is equal to eta. Yes? To eta, or if you pass it on the other side, we get 1/2. I mean, I hope this reminds you something, right? Because this is precisely the SLD equation. Yes? So for all our problem, we had our curve rho V and the prior distribution P0 of V, and a priori we could consider many different measurements, or any basis for doing measurement. We can just find the optimal measurement by solving this kind of SLD equation. I mean, we don't call it SLD because there is no derivatives here, but it still has the same form as before, right? Before, remember, for QE5 we had the same story with rho, right? It was 1/2 rho S, well, that we call D. So So it has a very similar mathematical structure. Let's do this equation we encountered before. With the only difference that now these guys are not local properties, gamma and s, gamma and beta, but really gamma now is kind of the average state. Okay, and beta is the first moment operator, so to say. So yeah, there is a big difference we have to understand in this operator is that this operator really knows about the whole curve. Right? So if you have this curve over B, really, because this is an integral over the whole curve of the states. This as well, just the integral of the whole curve. So these are kind of global operators on the whole curve. Whereas these guys are just local at one point. Nevertheless, kind of the mathematical structure is very similar, which is amazing. Yes, and finally, of course, by plugging it back in our expression, I just recall you that then we get the expected variance. Once we solve this equation, the expected variance will just be. So let me just check the note. So because we raised the expression already. The expected value will be just. Expected variance will be the prior second moment minus trace of beta times s. Yeah. Same as it was. This term is like for the QFI, right? Rho dot times symmetrical integrated. So just to conclude the first hour, the important thing here is that you really understand the difference of what we're doing now with what we did before. Before we consider always really estimator and how its value fluctuates around the fixed value of the field. So it was really just a local property of this curve. But now here we managed this curve to derive the same sort of mathematical formalism here, but for these global operators. Of course, now the restriction here is we only consider projective measurements. So this is just much more complicated, in fact, if you don't consider projective measurement. And in general, we don't know if it's optimal. So. Yeah, that's the price to pay to do this. Also, these things have to be computed, right? They really depend on the prior. So here the prior can change the solution. Yeah, so now we really use this theory to take some intuition about this result. I think we will do it in the exercises, right? So we'll get an exercise where we see a bit how these things work and how it relates to the QFI, right? And I think we can do it just with a qubit or two to make it simple. So I think we take a break now, right? And then continue.